every single day. We wake up to it. We plan our outfits around it, sometimes rearrange our whole weekends because of it. And honestly, it can really affect our mood.
Definitely.
I'm talking, of course, about the weather. One minute it's just glorious sunshine. The next there's a sudden downpour. Seems like it came out of nowhere.
Uh-huh.
But have you ever really stopped to wonder why it feels so, well, personal sometimes and so unpredictable? Why does it swing so wildly, even within the same season? It just defies what we think winter or summer should be like.
Yeah, like wearing a heavy coat one day and just a hoodie the next. Right.
Yeah.
And it's still February.
Exactly. What is going on up there?
It really is an age-old puzzle, isn't it? Our lives are so tangled up with these atmospheric shifts, but the how and why often feel a bit mysterious.
Totally.
So our goal today is really to unravel some of that for you, to give you the insights to maybe understand the skies conversation a bit better. We're going to dive into the atmosphere's dynamics, the science behind those daily changes, the huge role clouds play, the art, and the limits of forecasting, and crucially, that big difference between weather and climate.
Okay, let's do it. Let's unpack this unpredictable dance. We talk about the weather constantly, but if you had to pin it down, give a precise definition, what is it?
Well, simply put, weather is all about the short-term conditions in the atmosphere.
Right term. But...
Yeah, things like temperature, humidity, rain or snow, wind, how cloudy it is, all those things that change hour by hour, day by day. It's incredibly dynamic. So if you think of seasons as setting the background rhythm, like the main theme of the music, then weather is more like the improvised melody playing over the top, full of unexpected twists and turns.
I like that. Improvised melody. That really captures it. So if weather is this improv, what are the main drivers, the forces causing those sudden shifts, even if it's supposed to be one season?
Okay, so there are a few key players constantly interacting. First, you've got air masses. Just imagine these huge blobs of air, right? Each one has its own distinct temperature and moisture.
Right, like a big bubble of cold, dry air moving down from Canada.
Exactly like that. And when these different air masses move and collide, that's when the weather really shifts dramatically.
Yeah.
And the boundaries where they meet, those are called fronts. Cold fronts, warm fronts, they bring those really sudden, noticeable changes we feel on the ground.
Oh, yeah, I swear, I can sometimes feel a cold front coming. That sudden drop in temperature, the wind picking up.
You absolutely can. Then, way up high, you have the jet stream. These are powerful winds like rivers of air that basically steer storm systems and those big air masses across continents. A small change, a little wiggle or dip in the jet stream can mean completely different weather for places quite close to each other. Maybe a snowstorm here while a city nearby gets sunshine. And then don't forget local geography. Things like mountains act as barriers. They can force air up, making it release moisture, creating rain shadows on the other side.
Right.
And large bodies of water, like the oceans or the Great Lakes, they moderate temperatures. That's why coastal areas are often milder in winter than places further inland.
It's amazing how all these invisible forces work together. So that experience of needing a heavy coat one day and just a light jacket the next, even in the same season, that could just be a front blowing through or the jet stream taking a different path.
Precisely. Or think about those weird spring snowstorms that catch everyone off guard.
Ugh. Yes.
That's often the jet stream dipping much further south than usual, dragging that cold Arctic air down with it. And those sudden, intense summer thunderstorms. That's usually warm, moist air rising really fast, condensing, and building up into those massive thunderclouds.
It really shows how nature doesn't fit neatly into our boxes, does it? We expect winter to be just cold, but the atmosphere is always improvising.
Exactly. It resists those rigid categories.
Yeah. So what's the big takeaway for us then, trying to navigate this?
I think it's a constant lesson in adaptability. Seasons give us a general idea, sure, but the day-to-day weather, it's always reminding us to be ready for a surprise. It teaches us to watch, to be flexible.
Good point. And speaking of watching, you can't talk weather without looking up at the clouds. And you said they're not just decoration, they're like engines of weather.
Absolutely. Clouds are essentially where water vapor, that invisible gas, condenses and becomes visible. Billions and billions of tiny water droplets or ice crystals all clustered together.
So not just fluffy stuff floating around.
Definitely not. They play this incredible triple role. They help regulate Earth's temperature, they transport huge amounts of water across the globe, and crucially, they're like billboards for upcoming weather.
Billboards?
Yeah, visual signals, if you know how to read them. Looking at a cloud is almost like seeing the water cycle written across the sky.
That's a really nice way to put it. So, okay, beyond just looking interesting, what are these engines actually doing? What's their main job?
Well, they have several vital functions. First, like I said, transport. They carry water from the oceans over land, distributing moisture, essential for life.
Right.
Second, climate regulation. During the day, white clouds reflect sunlight back into space, which has a cooling effect. At night, they act like a blanket, trapping heat escaping from the Earth, which keeps things warmer.
Okay, so cooling and warming.
Exactly. And third, they're amazing weather signals. Their shape, their altitude, how they're moving these, all give clues about what kind of weather might be on the way.
And there are so many different kinds. It can feel a bit overwhelming. If you only have, like, a few seconds to glance up, what's the most important thing a cloud can tell you? Is there a quick way to tell if it's just a pretty cloud or a watch-out cloud?
That's a great question. You don't need to be a meteorologist memorizing Latin names. The key things to notice quickly are really height and density or thickness.
Height and thickness, okay.
Yeah, think of them in broad families. First, you have the high clouds, way up there, above 20,000 feet. These are thin, wispy, made of ice crystals. Like cirrus clouds, those feathery streaks. They usually mean fair weather for now, but they can also be the first sign that a weather system, maybe bringing rain or snow, is approaching in a day or so. They're like the advance warning.
Okay, so high and thin means change might be coming, but not right away.
Generally, yes. Then you have the middle clouds, roughly between 6,500 and 20,000 feet. These are thicker, usually made of water droplets, sometimes ice. Think of a grayish sheet covering the whole sky that might be altostratus.
Right, the kind that makes the sun look watery.
Exactly. And that often precedes steady, more widespread rain or snow. Or you might see altocumulus, those patches or clumps of white or grayish clouds. They can mean warm, humid conditions and sometimes signal thunderstorms later in the day, especially on a summer morning.
Okay, middle cloud's getting more serious.
Potentially, yeah. And finally, you have the low clouds, from the surface up to about 6,500 feet. These are typically the thickest, darkest, and closest to the ground. Stratus clouds give you that flat, featureless, gray, overcast sky, maybe with some drizzle.
Gloomy day clouds.
Pretty much. But the real rain or snow workhorses are the nimbostratus clouds. Thick, dark, ragged sheets that bring that steady, often prolonged precipitation.
Nimbostratus. Got it. Steady rain.
Exactly. And then sort of spanning all these levels, you have the vertical clouds.
Ah, the puffy ones.
Right. The classic cotton ball cumulus clouds usually mean fair weather. But when they start growing upwards, getting taller and taller, maybe developing that flat anvil shape at the top.
Uh-oh.
Yeah, then they become cumulonimbus. Those are the thunderheads. The powerhouse is responsible for heavy downpours, lightning, hail, sometimes even tornadoes. They're the dramatic ones.
Okay, so height and thickness are key. High and wispy, maybe change later. Low and dark, probably precipitation now or soon. And tall and towering, watch out for storms.
That's a really good quick summary.
Yeah. It's amazing how much variety there is. You mentioned height and water content, but what else makes them look so different? Like, why are some flat and others puffy?
Great question. Air movement is a huge factor. Smooth, stable air tends to create those flat, layered clouds like stratus. But if the air is rising rapidly and is unstable or turbulent, you get those vertical, puffy shapes like cumulus and cumulonimbus.
Okay.
Water content definitely matters, too, generally. The more water or ice a cloud holds, the thicker and darker it appears because less sunlight gets through. And then, of course, the angle of the sun plays a role, especially at sunrise and sunset, creating all those amazing colors as light scatters differently through the droplets or crystals.
So they really are telling a story up there, aren't they? Like a silent forecast if you learn the language.
Absolutely. Pilots, farmers, sailors, they've always relied on reading the clouds. And anyone can learn the basics. It's also kind of a reminder of impermanence, you know. Clouds are always changing, shifting, forming, and dissolving. When we look at them, we're not just seeing weather, we're seeing the physical form of water in the atmosphere, constantly cycling.
Yeah, that's true. So the big takeaway on clouds is they're the sky's storytellers. Each type plays a part, whispering fair weather or warning of storms. Not just pretty backdrops, but vital players carrying water, shaping climate, painting that constantly changing canvas above us.
Beautifully put.
Okay, let's take this a step further. From these clouds being storytellers to being the actual birthplaces of rain. And even the fuel for really extreme weather. Because it all starts in a cloud, right?
Absolutely, yes.
Right.
Every drop of rain, every snowflake, it begins inside a cloud as tiny water droplets or ice crystals bump into each other and grow. They keep growing until they're heavy enough to overcome the air currents holding them up, and then they fall.
But why is some rain just a gentle drizzle that lasts for hours, and other times it's like a torrential downpour that floods streets in minutes?
It really comes down to the type of cloud and the dynamics inside it. That light, steady rain or drizzle. That usually comes from those layered, flatter clouds like stratus or nimbostratus, where droplets form relatively slowly and aren't very large.
Huh?
But those intense downpours, they typically come from cumulonimbus clouds, the thunderheads. Inside those clouds, you have incredibly strong updrafts, currents of air rushing upwards.
Right.
These updrafts can hold onto water droplets for much longer, allowing them to grow much, much larger before they finally become too heavy and fall all at once. That's why you get such intense bursts of rain.
So the cloud's internal engine makes all the difference. And you mentioned clouds don't just release water, they release energy. How does that work? How is water fuel?
This is absolutely key, especially for understanding storms. Remember how clouds form from water vapor condensing into liquid droplets or ice crystals?
Yeah.
That process, condensation, actually releases heat into the surrounding air. It's called latent heat.
Latent heat. Okay.
And this released heat warms the air, making it more buoyant, causing it to rise faster, which can lead to stronger updrafts, which pulls in more moist air, which leads to more condensation, releasing more heat. It's a feedback loop.
Wow.
So water vapor isn't just passive stuff getting carried around. The very act of it turning into a cloud releases energy that can power and intensify weather systems. It's literally the fuel.
That's incredible. Okay, let's talk about that fuel powering the really big events.
Yeah.
Like tornadoes.
Yeah.
How do they spin up inside these clouds?
Tornadoes are born inside the most intense thunderstorms, typically what we call supercells. These are massive, rotating cumulonimbus clouds.
The really scary looking ones.
Exactly. You need a specific recipe, lots of warm, moist air rising very rapidly, fueled by that latent heat release colliding with cooler, drier air. And crucially, you need wind shear.
Wind shear.
That means winds blowing at different speeds or directions at different altitudes. This difference in wind can start the rising column of air inside the thunderstorm rotating. If that rotation intensifies and stretches down towards the ground, you get a tornado.
And the water vapor is essential for that whole process.
Absolutely essential. Without that moist air and the energy released during condensation, you wouldn't get the powerful updrafts needed to sustain such a violent rotation.
Okay. And what about hurricanes? They seem like the ultimate example of water as fuel, forming over warm oceans.
They really are. Think of a hurricane as a gigantic heat engine powered entirely by water.
Wow.
It constantly sucks up warm, moist air evaporating from the ocean surface. As that air rises high into the storm clouds, the water vapor condenses, releasing enormous amounts of latent heat.
That feedback loop again.
Precisely. That heat release is what drives the storm's incredibly powerful winds and sustains its structure. The swirling clouds you see are the visible manifestation of this continuous cycle. Evaporation, rising air, condensation, heat release, stronger winds, repeat. Cut off the supply of warm water like when a hurricane moves over land, and it quickly loses its fuel source and weakens.
So water isn't just in the hurricane. It is the hurricane's energy source. Amazing. Now, just quickly, tsunamis, they involve huge amounts of water, but they're different, right? Not weather.
Yes, that's a really important distinction to make. Tsunamis are devastating water events, but they are not caused by weather.
Okay.
They're triggered by geological events under the ocean, usually large earthquakes, but sometimes underwater landslides or volcanic eruptions. These events displace a massive volume of water, creating waves that travel across the ocean. So the water is the destructive force, but the origin is tectonic, not atmospheric.
Got it. Weather versus geology. So when we look at everything from a light sprinkle to a catastrophic hurricane, the huge difference in intensity really boils down to how much water vapor is available, how much energy gets released when it condenses, and how unstable the atmosphere is.
That's exactly it. It's the specific combination and intensity of those ingredients, water vapor, latent heat energy, and atmospheric instability that determines the scale of the event. Clouds, in this light, really embody this duality, this power. They bring gentle, life-giving rain, but under the right conditions, fueled by water's energy, they can unleash devastating force. It's a potent reminder that the same substance that sustains life can also become incredibly overwhelming. Water in the sky is pure potential energy, sometimes a whisper, sometimes a roar.
That's a powerful way to think about it. So clouds aren't just pretty pictures. They are the engines of weather, the birthplace of rain, the fuel for storms, creating everything from mist to monsoons. They're the visible face of water's restless energy up there.
Perfectly said.
Okay, with all this complexity, all this energy swirling around, how on earth do meteorologists even attempt to predict what's going to happen next? Forecasting seems like an incredibly difficult job.
It absolutely is. It's a really sophisticated mix of science, cutting-edge tech, and pattern recognition. It starts with just massive amounts of observation. Right.
You've got satellites watching from space, weather balloons sending data back as they rise, radar scanning for precipitation, thousands of weather stations on the ground measuring temperature, pressure, wind.
So tons of data pouring in constantly.
Constantly. And all that data gets fed into incredibly powerful computer models. These run complex mathematical equations based on the laws of physics to simulate how the atmosphere, the air, the moisture, the heat is likely to move and change over time.
Simulating the future state of the atmosphere.
Exactly. And then the human element is still crucial. Experienced meteorologists look at these model outputs, compare the current situation to historical patterns, times when the atmosphere looks similar, and use their expertise to interpret the data and issue a forecast. So it's very much data-driven prediction, not just guessing.
But even with all that tech and expertise, forecasts aren't always perfect, are they? Why is it still so hard to nail it down sometimes?
Yeah, that's the million-dollar question. It really comes down to the fact that the atmosphere is what scientists call a chaotic system.
Chaotic, meaning it's incredibly sensitive to tiny, tiny changes in its initial conditions. It's the classic butterfly effect idea. A butterfly flapping its wings in Brazil could theoretically set off a chain of events leading to a tornado in Texas weeks later.
Okay, maybe not literally a butterfly, but the principle holds.
The principle absolutely holds. Even with all our observation tools, we can't measure every single variable everywhere all the time. There are always tiny errors or gaps in the initial data fed into the models.
Okay.
And in a chaotic system, those tiny initial uncertainties can grow exponentially over time, leading to forecasts that diverge from reality, especially further out. Plus, you've got local complexities, mountains, coastlines, even cities creating urban heat islands that are really hard to model perfectly.
So the further out the forecast, the more those small uncertainties can snowball.
Exactly. That's why forecasts are generally most reliable for the next 24 to 48 hours. They're still pretty decent out to maybe 5 or 7 days. But beyond that, you're really looking more at general trends and probabilities rather than precise day-by-day predictions.
That makes a lot of sense. Okay, speaking of probabilities, let's tackle that common weather app phrase, 30% chance of rain. What does that actually mean for me and my plans? Because it definitely doesn't feel like it rains 30% of the time on those days.
Right. This is probably one of the most misunderstood parts of a weather forecast. That percentage is usually the probability of precipitation, or POP.
Poppy.
And what it officially means is there's a 30% chance that any specific point in the forecast area, like your backyard or the park where you're planning the picnic, will receive measurable precipitation, usually defined as 0.01 inches or more during the forecast period.
Any specific point?
Okay. Another way meteorologists think about it is confidence X area. So it could mean the forecaster is 100% sure it will rain, but only over 30% of the forecast region. Or it could mean they're only 30% confident that rain will develop at all, but if it does, it might cover the whole area.
So it's a combination.
It often is. But the simplest way for you to think about it might be this. If you had 10 days with the exact same atmospheric conditions as today, on about 3 of those 10 days, you'd expect to get some rain at your location.
Okay, that's actually much clearer. It's about the likelihood of encountering rain, not how long it will rain or how much the area gets wet.
Precisely. It's a statement of probability for a specific point.
Got it. Another thing I've always wondered about is the sheer range of temperatures we see. How can the same planet have places that hit negative 40 degrees and others that bake at 120 degrees Fahrenheit? What drives those huge extremes?
Well, the ultimate driver is the uneven heating of the Earth by the sun, mainly because of the planet's tilt and its spherical shape. The poles get much less direct sunlight than the tropics.
Right.
Then the atmosphere and oceans act like a giant heat distribution system, constantly trying to balance things out, moving heat from the equator towards the poles. But it's a very inefficient and complex process. A huge factor is the difference between land and water. Land heats up and cools down much, much faster than water does. That's why continents tend to have much more extreme temperature swings between summer and winter, and even between day and night, compared to coastal areas or islands, which are moderated by the nearby ocean.
Ah, the water acts like a temperature buffer.
Exactly. And then you layer on things like mountain ranges, blocking airflow, altitude, it gets colder higher up, and those jet streams shifting masses of polar or tropical air around. All these things can combine to create really dramatic local and regional temperature extremes.
It's a complex interplay.
Yeah.
Now, about measuring temperature, we use Fahrenheit here in the US, while most of the world uses Celsius. Does using one scale versus the other actually change how we perceive the temperature?
That's a really interesting question, and I think it probably does, subconsciously at least. Fahrenheit, the scale Daniel Fahrenheit developed, is often described as being more human-scaled for everyday weather, at least in temperate climates. 0 was roughly the coldest he could easily achieve in his lab, and 100 was initially set close to human body temperature. So the 0 to 100 range conveniently covers most temperatures people commonly experience.
Right, it feels like a percentage of weather intensity sometimes.
Kind of, yeah. And because each degree Fahrenheit represents a smaller temperature change than a degree Celsius, you get more numbers, more granularity within that common range. Celsius, developed by Anders Celsius, is tied directly to the physical properties of water at standard atmospheric pressure. 0 degrees C is the freezing point, 100 degrees C is the boiling point. It's very logical from a scientific perspective.
That's
But because the Celsius degree is larger, 1 degree C equals 1.8 degrees arrow, the numbers don't sound quite as dramatic at the extremes, maybe. A scorching hot day might be 100 degrees arrow, which sounds really intense. The same temperature is about 38 degrees C, still very hot, but maybe the number 38 doesn't have quite the same psychological impact as 100 for someone used to Fahrenheit.
Yeah, 100 just sounds like a barrier.
Exactly. So while they're just different scales measuring the same physical reality, the numbers themselves and our familiarity with them likely do shape our perception a bit.
Fascinating. So, thinking about these probabilistic forecasts, the chaotic nature of weather, the wild temperature swings, it really brings home how much is beyond our direct control, doesn't it?
It absolutely does. I think weather is one of nature's greatest teachers of humility. We can observe it, measure it with incredible technology, build sophisticated models, prepare for it,
Yeah.
but we can't fundamentally control it. The best we can do is understand the probabilities, the tendencies, the risks.
Right.
So when you see that 30% chance of rain, don't think the forecast is wishy-washy or confused. Think of it as an honest reflection of nature's inherent uncertainty. Under those conditions, sometimes it rains at your spot, sometimes it doesn't. Forecasting is less about achieving perfect certainty and more about navigating the possibilities within this amazing, complex, chaotic system.
That's a really healthy perspective. Okay, let's shift gears slightly to tackle something that causes a lot of confusion. The difference between weather and climate. People use these terms interchangeably all the time, but they are definitely not the same.
Oh, absolutely. This is such a crucial distinction, especially today. So let's break it down simply. Weather, as we've been talking about, is the state of the atmosphere right now, or over a very short period, hours, days, maybe a week. It's what's happening outside your window today. Sunshine, rain, wind, temperature. That's weather.
Okay, short-term conditions, the improvised melody.
Exactly. Climate, on the other hand, is the long-term pattern of weather in a particular region. It's the average weather conditions plus the range of variations and extremes, typically measured over decades. 30 years is a standard baseline, or even centuries.
Long-term average patterns.
Right. Think of it this way. Weather is the outfit you choose to wear today based on the forecast. Climate is your entire wardrobe, reflecting all the types of weather you expect to experience throughout the year in your location.
That's a great analogy. Weather is today's outfit, climate is the wardrobe. Okay, so building on that, let's clarify two more terms that often get tangled. Global warming and climate change. Are they the same thing?
They're related but not identical, and the difference is important. Global warming refers specifically to the observed long-term increase in Earth's average surface temperature. It's primarily driven by the increased concentration of greenhouse gases in the atmosphere, largely from burning fossil fuels and other human activities. Think of it as the planet running a fever. The overall temperature reading is going up.
Okay, global warming, rising average temperature.
Precisely. Climate change is a much broader term. It encompasses global warming, but it also includes all the other effects that result from this warming trend.
Like the side effects of the fever.
Exactly like that. Climate change includes shifts in precipitation patterns. More intense rainfall here, deeper droughts there, changes in the frequency and intensity of extreme weather events, like heat waves, floods, powerful storms, melting glaciers and ice sheets, rising sea levels, ocean acidification, impacts on ecosystems. It's the whole suite of changes happening to the Earth's climate system because it's warming up.
So global warming is the primary driver, the temperature rise itself, and climate change covers all the consequences of that rise across the entire system.
You've got it. Global warming is the thermometer going up. Climate change is what happens to everything: rainfall, storms, ice, oceans, seasons, because the thermometer's going up.
Why is this distinction so important for people to grasp?
Because it helps address that common misunderstanding where someone experiences a particularly cold day or a snowy winter and says, see, global warming isn't happening.
Right, confusing weather with climate.
Exactly. A single cold day or even a cold season is a weather event. It doesn't negate the long-term trend of rising average global temperatures, global warming, or the broader shifts in the climate system, climate change. In fact, climate change can sometimes lead to more extreme swings, including potentially more intense cold snaps in some areas due to disruptions in things like the jet stream, even while the overall global average temperature continues to climb. It's about the whole pattern shifting, becoming less stable, more volatile.
That makes sense. It's not just uniform warming everywhere all the time. It's destabilizing the whole system.
Precisely. Destabilization and increased volatility are key aspects of climate change.
Okay, so weather is the daily mood, climate is the long-term personality, global warming is the rising fever, climate change is all the symptoms. That really clarifies things. Are there other important nuances between weather and climate?
Well, yeah, thinking about scale is useful. Climate determines what we generally expect. We expect deserts to be dry, rainforests to be wet. But weather is what actually happens day to day, and it can sometimes break those expectations, like that freak flood in a desert.
Right.
We also see climate variations on different scales. You have microclimates, like the conditions in a specific valley, or even the urban heat island effect, making a city warmer than its surroundings. And then you have large-scale macroclimate patterns, like El Niño and La Niña cycles in the Pacific, which influence weather patterns across huge parts of the globe.
And these things interact, right? Climate influences the type of weather we're likely to get, but can major weather events also influence climate trends?
Yes, through feedback loops. This is really important for understanding how climate change can accelerate. For example, warming temperatures, climate, cause Arctic sea ice to melt. Less ice means less sunlight is reflected away, ice is bright white, and more heat is absorbed by the darker ocean water. This absorbed heat further warms the region, leading to even more ice melt. That's a feedback loop, where climate change causes a weather surface change, less ice, that then amplifies the climate change.
Wow, a reinforcing cycle.
Exactly. Or think about how a massive wildfire, often made more likely by climate-driven drought and heat, climate-influencing weather, releases huge amounts of carbon dioxide, further contributing to global warming. It's all interconnected.
So the really worrying picture with climate change isn't just a gradual, gentle warming, but an increase in the frequency and intensity of these extreme weather events.
That's a critical point. It's not just about the average going up, it's about the extremes becoming more common and more severe. More record heat waves, more intense downpours leading to flooding, potentially stronger hurricanes fueled by warmer oceans, longer and deeper droughts. It's this volatility driven by climate destabilization that poses many of the biggest risks.
And this all filters down to us, right? Weather hits us, immediately affects our plans, our mood. Climate shapes things on a much bigger scale where we can live, grow food, build cities. It shapes history.
Absolutely. And while our personal experience of climate change often comes through experiencing these more intense or unusual weather events, it's so important not to mistake one heat wave or one storm for the entire long-term trend. We have to look at the decades of data.
So if weather is this guy's daily conversation,
Then climate is its autobiography, written over centuries.
that's powerful. What an incredible journey we've taken today, really diving into the daily surprises of weather, the vital role of clouds as these atmospheric engines, the challenges of forecasting, and then zooming out to the crucial long-term picture of climate.
It really covers a lot of ground, from the micro details to the big picture.
And what stands out most, I think, is that weather truly is this constant, unpredictable dance. A daily reminder that we need to observe, adapt, and just be ready for whatever the atmosphere decides to do.
Yeah, that adaptability is key.
So if there's one final thought to leave everyone with today.
I'd say maybe this. Weather is the dance we watch unfold every day, full of improvisation and surprise. Climate is the underlying music, the long-term rhythm guiding that dance across decades and centuries. Understanding both helps us see that every raindrop, every storm, every heat wave isn't just an isolated event happening today. It's part of this much longer, deeply interconnected story unfolding in the atmosphere all around us.
Beautifully put. So keep looking up. Hopefully after this deep dive, you feel a bit more equipped to understand, or at least appreciate, the incredible dynamic show happening above your head every single day. Keep observing, keep being curious.